Analogy that I use is paying for meter parking. So if you have to, feed the meter, put a coin in the meter to pay for parking, if you're familiar with that, you put a coin in that's worth 15 minutes of parking time, roughly. Maybe some places are a little cheaper where it's one coin or 25 cents is good for half an hour, maybe even an hour. All right. But let's say it's worth 15 minutes. So once the 15 minutes expire, then you have to put another 25 cents in. So now you're up to 50 cents for the second 15-minute period. Then you put another coin in, so another 25 cents. You're good to 45 minutes. The more coins you put in, the more time you get. All right. So that's the same idea here, except it's costing $40 for a period of 1 hour. All right. You could equate this to an hourly wage. Some places pay for a fraction of an hour, but most places pay for complete hours worked. So if you worked for 8 hours and 15 minutes, they pay you for 8 hours. It isn't until you hit the ninth hour that they pay you for the ninth hour. All right. So if you make $10 an hour, you make $10 for that first hour as long as you complete that first hour. It's a similar idea. All right. But in this case, the second the electrician starts work on the job site, $40 in the books. All right. Then once he reaches 1 hour worth of work, if he were to stop at that exact moment, all he would get would be $40. But going 1 second over, now he's got another $40. All right, so we want to model this in a graph. Well, the first thing, and maybe hopefully the most obvious, is that if he doesn't work any hours, he's not getting any money. All right. Now, the way this is scaled, 5 boxes gives you $100. So each box is worth $20. So 20, 40, 60, 80, and so on. Could label it up. So 1 second beyond zero time. So if he's on the job for 1 second doing work, the second he picks up a screwdriver, now he's got $40. So how do we represent a point that is very, very close to another point but doesn't actually touch it? We do that with an open circle. So we're going to say there's an open circle here at 0.40, and that for all the time beyond that, up to the 1 hour mark, he's going to get $40. The only period of time in which he won't get $40 would be for time t equals 0. If t is equal to 0, he hasn't done anything, so he doesn't get any money. But if t is equal to like a half a second, he gets $40. If it's equal to 15 minutes, he gets $40. If it's equal to 59 minutes and 59 seconds, he gets $40. If it's equal to 1 hour exactly, he gets $40. But the second he goes over, and that's a good thing, now he's up to $80. And he lives at the $80 price point until he's completed 2 hours worth of work. Right? So the open circle, again, gives us a location that we're getting very close to, but we don't actually make contact with. All right? It's just drawn in an exaggerated fashion, but this allows for 1.000000000000001 to be part of the set, just not 1. All right? To get really, really close to that value. Because it's kind of like, how can I plot a graph that shows 1.00000000001, comma 80? I get really, really close. I make a point here, like right there, maybe. And then somebody comes along and says, hey, is that 1, comma 80? I said, no, it's 1.000000. You get the idea. You know, so instead of doing that, we put the open circle there to indicate that we're getting really, really close to that point. We're just not going to actually touch it. All right. But then once we go a smidge over 2 hours, now we get another $40. So we're up to $120 until we hit the 3 hour mark. Once we go a smidge over 3 hours, now we're at $40 more, $160. And then once we hit a smidge over 4 hours, we're at the $200 mark. 5 hours of work, $200. Not too bad. All right. So actually, I mean, it's a little on the low side for an electrician, like a master electrician. That they do very well. So if you get an electrician that only charges $40 an hour to do work, then sign them up. Yeah. I mean, like you bring the car into the shop for work, they charge you. Usually, it's in the neighborhood of $75 an hour just for labor. Right? That doesn't even involve the parts. Right? So that's the same idea. $75 an hour for however many hours it takes to do the job. Right? So if they're changing out an engine, that could take many hours. They're going to charge you $75 for each one of those, and that doesn't even include the cost of the engine, the new engine that they're putting in the car. Right? So, but that's for any moment within that 1 hour period. You know, so now we want to write a piecewise function for this. I shouldn't have zoomed, or at least zoom there. We have 1, 2. Oh, let me just do it a different way. 1, 2, 3, 4, 5, 6 pieces. All right, so this will definitely be the biggest piecewise function that we've had so far, but it'll also be the simplest because each piece has a horizontal slope, except for this one, which is just a point. I'll show you how to handle that in a sec. But when you have a piece that involves a horizontal slope, it's just a y-intercept because remember the model is y equals mx plus b. If the m is equal to 0, then we're looking at 0x plus whatever the y-intercept is. So the result is just going to be the y-intercept. And the y-intercepts here are 40, 80, 120, 160, and 200. They're just multiples of 40. All right, so that should be easy enough. They said call it C. Reasonable to assume that we'll call this T. So C of T is going to be equal to, big old piecewise, we have points at 0, right? 40, 80, 120, 160, and 200. All right? All those y-intercepts. So a point can be thought of as a horizontal line that only exists at one point, at one particular x value. All right? So if I say when I talk about just a 0, I'm just going to say under what particular circumstance that 0 exists. C of t is 0, so the y value is 0 only if the x value is 0, so t is equal to 0. That's the only circumstance in which it's equal to 0. That's how we represent a point in a piecewise function. All right? This is the same as saying, so same as C of 0 is equal to 0, or just writing the ordered pair 0, 0. The second piece and all the remaining pieces, they happen over intervals. So if you just look at the second piece, you have an open circle on the left-hand side and a closed circle on the right-hand side. The t values that are relevant here are 0 and 1. So it's going from 0 to 1, open circle on the left, closed circle on the right. So I would say 0 is less than t, which in turn is less than or equal to a positive 1. Same idea for the 80. That goes from 1 to 2, open circle, closed circle. So 1 is less than t, which in turn is less than or equal to 2. Then just follow that trend. 2 is less than t, which is less than or equal to 3. 3 is less than t, which is less than or equal to 4. 4, that's not a 4. 4 is less than t, which is less than or equal to 5. And that would be your piecewise function. All right. Each one of these steps, they call it a step function, very creative. They're also known as brackets. All right. So when you think about it in a real world, a circumstance that exists that's kind of along these lines would be the concept of a tax bracket. So if you make a certain amount of money, you fall at a certain tax rate. Right? So if you make less than $50,000, you get taxed at this rate. If you make between $50,000 and $120,000, I'm just making up numbers. You're taxed at this rate, and you're at that rate for that interval of income. Right? So there are domains and function values associated with it. Right? I have it somewhere. I think I have it in one of my pre-calc lessons, but I'll maybe calculate. I'm not sure. But I'll pull it and you know what? It's in my, I know where it is. I'll find it and I'll show it to you sometime next week. It's pretty cool, but yeah, it's related to this, and I mean, if you think about it, I forget which class I talked about it. If it was this one, I apologize. But if you throw an object in the air and it's only impacted by gravity, then it goes up, it goes down, parabola. That's pretty easy. But if it's impacted by other factors, like aerodynamics, wind resistance, anything like that, then it could take on a different function, right? So it might go up in the path of a parabola, but then something may happen in terms of a spin, or, I mean, I don't want to get into all the different characteristics like yaw and stuff like that, but, the orientation of the object, the shape of the object, it could take on a different function. It may go linear at some point before coming down. You never really know, right? So, you think about somebody throwing a baseball. You think about the movement in Major League Baseball, the movement on a pitch. How do they get it to become a curveball, slider, cutter, whatever, changeup? Like all the different action on a pitch. It's not just a simple parabola. There's other functions at work there. If you want to model it, how would you go about doing that? You piece together different functions that you're familiar with, all right? And this is the beginnings of that. It's a little notation heavy, but it's very practical and very useful. All right, so.